Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillahilladzi hadana li hada wa ma kunna linahtadiya laula an hadanallah. Asyhadu an la ilaha illallah wa asyhadu anna Muhammadan abduhu wa rasuluh. Allahumma shalli ala Muhammad wa ala alihi wa ashabihi wa man tabi'ahu bi ihsan ila yaumiddin, amma ba'du. Fine, we discuss about mathematical modeling in process control. Mathematical modeling in process control. Modeling in process control. Here. Before we discuss about mathematical modeling, we review that we have studied about the variable, that we know about the variable. We have the classification of variable, input variable. We have the input and the output variable. In input variable, we have two types of input variable. That's a load variable and the manipulated variable. It is our input variable here. And then in output variable we have measured variable and unmeasured variable. Okay, we have studied this in our lecture before, and then I will illustrate you another classification of variable or another variable that we call the state variable. What is the state variable? How we know about the state variable? The variable that we can state or we can measure is temperature, pressure, composition, and then the flow rate, maybe. In this time, we have the basic or the fundamental quantities. The basic or fundamental quantities. What is the basic or fundamental quantities in chemical engineering? Do you know about the mass and the energy and the momentum? That is the basic or fundamental quantities. But unfortunately, in these quantities, we cannot measure directly. We cannot measure mass, energy, and momentum indirectly, but we can measure this variable. We can measure temperature, measure pressure, we can measure composition, and then we can measure the flow rate. That is the state variable. In the process, we have the state variable to state the process, the condition of the process, to show the condition of the process. Okay, that is the state variable. Okay, we know here that the state variable, that is the T, temperature, pressure, X, and flow rate, it can form the differential term or in accumulation term. It can be in accumulation term. That is the state variable. Beside the state variable, we have the state equation. We build this state equation using the conservation law. It can be conservation of mass, conservation of energy, and then conservation of momentum. And now we start modeling. We come from general equation. The general equation, that is rate of accumulation equal to rate of input. That is the general formula. Rate of output plus rate of generation. Okay. We apply this equation to the three conservation here. Rate of accumulation of mass, rate of input of mass, rate of output of mass, and rate of generation of mass. Rate of input, rate of accumulation of energy, and then similar to the energy and the momentum. Okay, that is the formula. And then we start using example of the CSTR. Do you know CSTR? Continuous state tank reactor. We have the reactor here. That is the tanks. Then start, and this is the input. We have the flow rate of input is Fi, and then Ti, and then Cai. That is the input time. And then we have the output here. The flow rate is F, and the composition is Ca, and the temperature is T. And then we have the jacket here for the coolant, like this. This is the coolant in, F coolant, in temperature coolant in, and then that is the coolant out, the temperature of coolant out is TGO. Okay. You have here, that is our system. And then we start to identify the unit of the system. We have the F, and then the Fi, and then the F coolant. The unit of this quantity is volumetric per unit time. Volumetric per unit time. Volumetric per unit time. And we have the concentration Ca and Ca input. The unit of this quantity is mole per volume. Okay. And then we make an assumption. We have an assumption here. The firstly, our assumption is Firstly, our assumption is mixing, perfect mixing. What is the implementation of this assumption? Because we have the assumption this, so the temperature in the reactor is same, exactly same to the temperature that output from the reactor. So the temperature in the reactor is the T, and the concentration in the reactor is Ca. Because we assumption that the mixing is perfectly. Okay? So we have another assumption, that is, we assume that the rho and the Cp is constant. We assume the temperature, the rho and Cp is not function of temperature. This is the constant. And we have another assumption too, that the reaction of A into P is the first order reaction. First order reaction and exothermic. Exothermic reaction. Okay, that is our assumption. And we add the assumption again that the insulation is perfectly. So there is no heat loss. We assume there is no heat loss. Okay, that is our assumption from this system. Okay, then we start to analysis. We start from overall mass balance. Overall mass balance. We have here the rate of accumulation equal to rate of input minus rate of output. Okay, there is no generation in mass, because the conservation of mass, there is no generation. Mass cannot be generation and cannot be disappear. So we have here the representation of the mass is volume multiplied by the rho, that is the mass, and the accumulation is the term of t time, that's equal to Fi, that is input, multiplied by rho, and then F multiplied by rho. You can see this. That is the input, that is the output. Okay? Because the rho is constant, so we can construct here the rho dV dt equal to Fi rho minus F rho. And we can remove the rho. So we have the equation, the final equation is dV dt equal to Fi minus F. That is the first way our first equation here. From overall mass balance, we get the diffusivity equal to Fi minus F. Okay. And then we continue to the component mass balance. In component mass balance, for component A, for component of A, mass balance, here, we use the same formula, rate of accumulation of component A equal to rate of input of component A minus rate of output of component A plus rate of generation of component A. In terms of component, we have the generation and loss because the mass of the component is converted into another component but not disappear or generation. Okay, in accumulation, we have the concentration Ca multiplied by volume of the reaction of the reactor here. The accumulation here is the concentration in this reactor multiplied by volume of the reactor. Okay, that is the mass, that accumulation VDDT equal to the input Fi multiplied by Ca input, and the output is F multiplied by Ca, and the generation is the reaction, that is minus Ra for multiplied by volume of the reactor, volume of the reactor. Focus on this formula. The Ca and the V is changed by the time, so there is no constant here. So from this formula we can use the mathematical equation fundamental, the Ca dV dt plus the V dCa dt equal to FICAI minus FCA plus min RI multiplied by V, volume of the reactor. And you can see this, the dVdt, and we have the formula of dVdt in the formula 1. So we can substitute this formula using the equation 1. So we have the Ca multiplied by F I minus F, that is the formula 1, and plus V dCa dt equal to FICAI minus FCA plus minus Ra multiplied by V, volume of the reactor. Here we have the FICA minus FCA plus V dCa dt equal to FICAI minus FCA plus minus Ra, and then volume of the reactor. We have here that FCA, we can remove the FCA, and then we can reorganize our formula that the phase dCA dt equal to FICAI minus FICA plus minus RA, the formula multiplied by phi, volume of the reactor, and then we can reorganize again the CCA dt equal to Fi divided by phi multiplied by CAI minus CA and plus minus RA. Okay, we divide here using the phi. That is the equation of second. That is the equation of second. The dCA dt, the equation of second. Okay, clear enough? That's good. We continue to the we have here the CA. We have the equation of CA. The equation of CA, we can use the Arrhenius equation, that the minus RA equal to KO multiplied by exponent minus energy, activation energy, divided by R and T, and then multiplied by the concentration, I think. That is the 2.A equation, you can say this. Okay, that is the addition equation for the equation of 2. Okay, and then we continue to energy balance. The energy balance. We use the same formula. The rate of accumulation of energy equal to rate of input energy minus rate of output the energy, and then minus the energy that or heat, the energy or heat that removed by the coolant, heat or energy. Okay, we call this energy or heat, remove by coolant, and then plus the energy that generation by the reaction from exothermic reaction. Okay, that is the formula of energy balance. And then from this we explain part into part. Rate of accumulation, we have the rate of accumulation. Okay, that is our formula. The energy of or the heat is mCpt. We have this. So the M is rho multiplied by volume. We can so this that in the reaction in the reactor we have the volume. So we multiply by rho, and then we calculate and then multiply by Cb, and then the temperature in the reactor. That is the heat energy of the fluid from the fluid in the reactor. So that the accumulation term here equal to Fi rho Cp Ti minus F rho Cp T minus the key, that is the energy removed by coolant, yeah, and then plus minus RA multiplied by delta H, yes, and then multiplied by the volume of the reactor. Okay, that is our formula here. We can simplify this formula by division by rho Cp. So we have the ddt of phi t equal to Fi multiplied by Ti minus F multiplied by T minus Q multiplied by rho Cp, and then plus Ra and delta H and volume, then divide by the rho Cp. Okay, we divide this formula using rho Cp. We know this, the phi, volume, and the temperature is function of time, so we can explain here that the phi dt plus T dv dt, that's equal to Fi Ti minus Ft minus Q per rho Cp, then plus Ra delta H volume and rho Cp. Okay, that is our formula. And then you know this, the dv dt from the formula 1, from the equation 1, we can replace this by Fi minus F. Okay, so we have the formula here that phi dt plus T Fi minus F equal to Fi Ti minus Ft minus Q per rho Cp plus Ra delta H on volume, and then the rho Cp. Okay, you can see this, that we have the Fit minus Ft equal to the phi dt equal to Fi Ti minus Ft minus Q per rho Cp, and then plus the Ra delta Ha and phi, and then but the rho Cp. You know this, we can remove this formula and then we reorganize this into the right side, and then we get the formula, the new formula of the dv dt equal to Fi Ti minus Ft Fit, and then minus the Q per rho Cp, and then plus Ra delta H, and then the phi, and then the rho Cp. Okay, and we can divide by phi. So we got we get the dt equal to fi per phi ti minus t, and then minus q per rho cp phi, then plus rho ra, then delta h, and then the phi per rho cp, and then phi. So we can remove the phi here. So we got the final formula, that is the dt, the differential of temperature is fi per phi, the ti minus t, minus q per rho cp phi, then plus rho, that's the ra reaction, and then the delta H, and then the rho cp, okay, and then the rho cp. Okay, that is the formula 3. We got this, the formula 3 here. Okay, so we have the dv dt, dca dt, and dv dt, the formula 1 dv dt, and then the dca dt, and then the dt dt. Okay, we got this. Do you know about the q? Q is equal to, this is the equation addition, that the q is F coulomb multiplied by rho, and then the cp, and then multiplied by the temperature coulomb output minus temperature coulomb input, or delta T. That is the Q that removed by Coulomb. So this is the formula 4. Yeah? You can see this, the formula 4. Okay, we resume our formula, that we have the firstly the dv dt equal to F minus F input minus F, and then the second we get the dca dt equal to, what is the dca dt? Fi, yes, Fi cii minus okay, Fi per phi cai minus ca output, and then plus reaction, and then plus minus Ra on the reaction. And then the formula 3 is the temperature, differential of the temperature. Because this, the differential of the temperature is Fi per phi, the Ti minus T, minus the Q per rho Cp phi, and then plus the Ra reaction, and then the delta H of the reaction, and then rho Cp. Okay, then rho Cp, yes, okay. And the addition formula, the 4, is that the Ra is Ko, or yes, the Ko, and then Ca, and then exponential the ART. And then the 5, that we have the key is equal to F Coulomb multiplied by rho multiplied by Cp of the Coulomb multiplied by the temperature difference of the Coulomb output minus the Coulomb of the Coulomb input. So we got this 5 formula, and we want to identify the variable. What is the input variable? The input variable, where is the input? We get this Ci, Cai, and then Ti, and then Fi, and then what is the Q? We can see the Q. So we not say the detail of the Q. So we just call this the Q as formula, and then the F. It can be output variable and it can be input variable when we use the formula the F as the manipulated variable. We have discussed this in the our lecture before. Okay. So, and then we have the output here. What is the output that we have? The what we have the output? The output variable is the phi volume of the liquid in the reactor, and then the Ca, and then the temperature output of the reactor. Okay, we identified the control variable and the manipulated variable. What is the control variable? The control variable, it must be the output variable. Come from here. The control variable, it can be, that is common, that the phi volume and then the temperature. Volume of the reactor, volume of the reaction, volume of the liquid in the reactor. What the parameter refer to this variable? Volume refer to Fi or F. Okay, and then the temperature refer to the key. So we can make this as the manipulated variable. So this is the load variable. Okay, so this is our variable here, manipulated variable, and then the load variable. Okay, it is clear enough, I think. Okay, that is the illustration of the modeling in mathematical modeling in process control that we have studied here. And you notice we have a sample of continuous state tank reactor that using coolant as the coolant agent, and then coolant agent, and then that is the our assumption, and then finally we got 5 equation here. The dVdt equal to Fi minus F, and then the dCAdt equal to Fi divided by the phi, and then Cai minus Ca plus Ra, and then the dt dt, or the temperature difference, or the temperature differential by the time, equal to Fi plus Fi divided by the phi, and then the temperature input minus temperature output, and then minus the Q, the heat removed by coolant, heat removed by coolant. You know this, heat removed by coolant, and then that is the heat of reaction, as addition. And then we have the reaction formula by Arrhenius, and then we have the Q by the mass of the coolant multiplied by the temperature difference of the coolant. And finally we got our load variable, that is the load variable environment, and we chose this as the manipulated variable. And the control variable, usually or commonly, is always the temperature and the volume. Okay, it is clear enough, I think. Thank you very much for attention. We continue to the next topic. That's all. Assalamualaikum warahmatullahi wabarakatuh.